When we think of the search for life, our minds usually go to warm, comfortable places. We imagine worlds like our own basking in the Goldilocks zone of a star, an area not too hot and not too cold where liquid water can happily exist on the surface. We think of jungles, oceans, and sunlight. This is why for a long time Mars was the primary candidate. It's relatively close and we know it was once warmer and wetter. So it seems like a deep contradiction, a paradox, that modern science is now investing so much hope and so many resources into exploring moons in the deep frozen outer solar system. We are sending multi-billion-dollar missions to places like Europa, a moon of Jupiter, and Enceladus, a moon of Saturn. These worlds are solid balls of ice. Their surfaces are among the coldest places in the solar system, hundreds of degrees below zero. They receive almost no sunlight. They seem like the very last places life could ever take hold. Why are we looking there? The answer is that we have learned to change our definition of habitable. The search for life stopped being just about following the sunlight and became about following the water, no matter where or how deep it is hidden. The first revolutionary clues came from Jupiter's moon Europa, primarily from a spacecraft called Galileo, which orbited the giant planet in the 1990s. From a distance, Europa looks like a smooth white billiard ball covered in long, mysterious reddish-brown cracks. Scientists first noticed something very strange about its surface. It's young. In our solar system, an old surface is like an old face. It's covered in pockmarks and craters from billions of years of impacts. Our own moon is covered in them, but Europa has very few. This lack of craters implies that the moon is being resurfaced. Something is constantly smoothing it out, erasing the old impacts and creating a fresh new coat of ice. This was a strong hint that the ice shell we see isn't a static solid block, but rather a dynamic crust. We saw more evidence in the shapes of the ice itself. The surface is covered in long parallel ridges and vast jumbled regions called chaos terrain. This terrain looks exactly like what you'd get if you took a field of icebergs, floated them in slush, and then let the whole thing freeze solid again. It strongly suggested that the entire ice crust of Europa is decoupled from the rocky core below. It's floating, but floating on what? The Galileo spacecraft provided the most powerful piece of evidence, and it came from an invisible force magnetism. Jupiter has an incredibly powerful magnetic field that sweeps past Europa as the moon orbits. Galileo carried a magnetometer, an instrument designed to measure magnetic fields. When it flew past Europa, it detected a blip, a distortion in Jupiter's magnetic field. This new induced magnetic field was coming from Europa itself. How scientists know that if you pass a changing magnetic field over an electrical conductor, it creates or induces a new magnetic field inside that conductor. Galileo had found the signature of a conductor. So what on Europa could be conducting electricity? Solid freshwater ice is a very poor conductor. The moon's rocky core might be a conductor, but the signal wasn't a perfect match for a rock core. The data fit one model almost perfectly, a global globe-spanning ocean of liquid salt water. The salt is the key. It makes the water an excellent electrical conductor. The data suggested that miles beneath the frozen cracked surface of Europa, there is a hidden ocean of liquid water, an ocean that could potentially contain more than twice the amount of water in all the oceans on Earth combined. The paradox was beginning to unravel. We were looking at Europa not because its surface was warm, but because its interior was. This ocean is kept liquid not by the sun, but by tidal heating, the constant gravitational squeezing and stretching from Jupiter, which acts like a friction brake, generating enough heat deep inside to melt the ice. While the evidence for Europa's ocean was and is overwhelming, it was still indirect. We inferred the ocean from magnetism and geology. We hadn't seen the water. Then we went to Saturn and everything changed. The Cassini spacecraft, arriving in 2004, turned its attention to a tiny, seemingly insignificant moon called Enceladus. This moon is incredibly small, only about 310 miles, 500 kilometers across. It should have frozen solid billions of years ago. Instead, Cassini found that its south pole was strangely hot. Even more stunning, as Cassini flew past it, saw massive geysers or plumes of material erupting from the surface and shooting hundreds of miles into space. These plumes were traced back to a series of long, parallel cracks in the South Pole nicknamed the Tiger Stripes. This was the smoking gun. This wasn't an inference or a magnetic signal. This was a tiny moon actively spraying its insides out into space. Cassini was even able to fly directly through the plumes to taste what they were made of. The results were astounding. The plumes were almost entirely water H2O vapor and tiny ice crystals, but they also contained simple organic molecules like methane, as well as carbon dioxide and ammonia. This was direct, unambiguous proof of a liquid water ocean hiding beneath the ice of Enceladus. But Cassini found one more ingredient that changed the entire game. Buried in the data from the plumes, scientists found silicon nanoparticles, tiny grains of sand or rock. There is only one way to get tiny grains of rock from the moon's core suspended in water and sprayed into space. The liquid water at the bottom of that ocean must be hot at least 90 degrees Celsius or 94 degrees Fahrenheit, and it must be actively churning against the rocky core. This discovery was the final piece of the puzzle. It painted a picture of hydrothermal vents at the bottom of Enceladus's dark ocean. This is the exact same environment, deep, dark and superheated by chemical energy from rocks, where many scientists believe life may have first begun on our own planet. The cold paradox was solved. We look for life on these icy moons, not despite the cold, but because the cold creates a protective shell, and beneath that shell, these moons have the three essential ingredients for life as we know it: liquid water, a source of energy, tidal heat and chemical vents, and the organic chemical building blocks. Europa hinted at it, but Enceladus proved it. When we look out past the asteroid belt, past Mars, we enter the realm of the giants. Here the sun is just a bright star, its warmth almost meaningless. We are in the deep freeze of the solar system. The moons orbiting Jupiter and Saturn should be nothing more than dead balls of rock and ice frozen solid for billions of years, and yet they are not. We see evidence that defies this cold logic. We see moons with surfaces that are smooth and cracked like the ice on a shifting polar sea here on Earth. We see plumes of water vapor and ice crystals erupting from the south pole of Saturn's tiny moon Enceladus, shooting hundreds of miles into space. We measure the magnetic field of Jupiter's moon Europa and find that it behaves exactly as you would expect if there were a massive global ocean of salty, conductive liquid water sloshing around beneath its frozen crust. This discovery presents us with one of the most profound questions in modern astronomy. In this darkness and this cold, how does the water stay liquid? The sunlight can't do it. The moons are too small to have held on to heat from their formation like the Earth did. The answer is not heat from the outside, but heat generated from the inside. The answer is a process called tidal heating. It is in effect a perpetual engine. It's an engine that runs not on fuel or light, but on the pure, relentless force of gravity and motion. To understand it, you can perform a simple experiment right here on Earth. Take a metal paperclip, hold it and bend it back and forth and back. Within seconds, if you touch the bend, you will feel that it has become hot. This heat is not magic, it's friction. You are forcing the metal crystals inside to rub against each other, and that friction generates thermal energy. Now imagine this same process on a cosmic scale. In this scenario, the paperclip is a moon like Europa. The hand bending it is the colossal gravity of its parent planet Jupiter. Jupiter is the king of our solar system. Its gravitational pull is so immense that it doesn't just hold its moons in orbit. It actively squeezes them. This pull is not uniform. Gravity depends on distance. Jupiter pulls on the near side of Europa, the side facing it, much more strongly than it pulls on Europa's centre. And it pulls on Europa's centre more strongly than it pulls on the far side. This difference in pull is called a tidal force, and its effect is to stretch the moon. It constantly pulls Europa out of a perfect spherical shape and into a slight oval like a water balloon. Now, if Europa had a perfectly calm, perfectly circular orbit, this wouldn't be a big deal. It would be stretched once, lock into that shape, and then eventually cool down. The bending of the paperclip would stop. But Europa's orbit is not a perfect circle. And the reason why is perhaps the most beautiful part of this entire mechanism. Europa is not alone. It is locked in a precise mathematical rhythm with its neighbours. This is called an orbital resonance. It is a cosmic dance. For every one time the great moon Ganymede orbits Jupiter, Europa orbits exactly 2 times. And for every 2 times Europa orbits the volcanic moon Io, orbits exactly 4 times. They are linked 1, 2, and 4. This perfect timing means that the moons regularly line up in space, passing each other at the same points in their orbits over and over again. Every time they pass, they give each other a little gravitational kick. This constant rhythmic kicking prevents any of the moons from settling down into a relaxed circular orbit. It forces their orbits to remain slightly elliptical, a slight oval. This is the key to the entire engine. Because its orbit is an oval, Europa's distance to Jupiter is always changing. For part of its orbit, it swings a little closer to the giant planet, then it swings a little farther away. When it swings closer, Jupiter's gravity intensifies and the moon is stretched more. When it swings farther away, the pull weakens and the moon relaxes back. This is the back and forth bending of the paperclip. Stretch, relax, stretch, relax. This cycle repeats every 3.5 Earth days. It has been happening without pause for over 4 billion years. Imagine the sheer unimaginable amount of friction this generates. The moon's rocky core is constantly being flexed and squeezed. Its deep layers of ice are ground against each other, and all of that friction generates heat. This internal heat born from gravity and rhythm radiates upward from the moon's core. It has nowhere to go. It becomes trapped beneath the moon's thick insulating outer shell of solid ice. The surface of Europa remains one of the coldest places in the solar system, hundreds of degrees below zero. It is a perfect shield of ice, perhaps 10 to 15 miles thick. But underneath that shield, the constant heat from the tidal engine is more than enough to melt the ice. It doesn't just create a lake or a small sea, it creates a global liquid water ocean. An ocean that is dark, hidden, and vast. It's estimated that Europa's subsurface ocean may be over 60 miles deep and contain more than twice the amount of liquid water found in all of the oceans of Earth combined. The same process is at work on Saturn's moon Enceladus, where the tidal flexing is so violent it cracks the moon's south pole, venting that hidden ocean directly into space as towering geysers. This is the magnificent result of the perpetual engine. It shows us that the necessary ingredients for life, liquid water and energy, are not confined to the warm, sunlit regions of a solar system. They can exist in the cold and the dark, powered by a hidden engine of gravity. It forces us to rethink where we might find life not just in our solar system, but across the entire cosmos. We have found our ocean. It is a quiet, dark and potentially warm place hidden beneath a thick shield of ice on a distant moon. It is the first requirement, the cradle. But a cradle is just an empty box until something is placed inside it. Water is the stage, but it isn't the actor. Life as we know it is a process. It is active, it builds, it consumes, it moves, and it copies itself. All of that action requires one essential thing: energy. Here on Earth, the dominant source of energy is the sun. Plants breathe in the sunlight using photosynthesis, a word that means making things with light. We eat the plants, or we eat the animals that eat the plants. Nearly every living thing on our planet's surface is part of this vast chain, powered by a star 93 million miles away. But our hidden ocean on that distant moon is trapped in permanent darkness. The ice ceiling might be 5, 10 or even 20 miles thick. The faint light from its distant sun cannot possibly reach these depths. If life is to begin here, it must be powered by something else. It needs a different kind of food. It needs chemistry. This brings us to the second vital ingredient. Life isn't just energy, it is also stuff. You are made of building blocks atoms like carbon, hydrogen, nitrogen, oxygen, phosphorus and sulfur. A simple ocean of pure water, just H2O, is sterile. It's a clean room. Life is messy. It needs a supply of these raw materials. So where does this energy and this stuff come from? The answer, we think, lies at the bottom. We must look to the floor of that ocean. Let's imagine what is happening there. This moon is not sitting still. It is in a constant gravitational tug-of-war with its giant parent planet. This endless squeezing and stretching, this tidal flexing, churns the moon's interior. Deep below the ocean floor in its rocky core, this friction generates immense heat. Now picture the seabed. It is not a smooth, perfect sphere. It is cracked and fissured. The cold water of the ocean, driven by immense pressure, seeps down into these cracks. It trickles miles deep into the hot, rocky mantle of the moon. As the water gets closer to the hot core, it changes. It heats up, eventually becoming superheated, far hotter than the boiling point of water on Earth's surface. And this superheated water becomes a powerful solvent. It is aggressive. It strips the rock of its chemicals. It dissolves minerals, metals, and simple compounds. It pulls sulfur, iron, and hydrogen out of the stone. This water is no longer just water. It is now a hot, dark chemical soup rich with minerals and loaded with potential energy. Because it is so hot, this water is now less dense than the cold water above it. So it begins to rise. It races back up through the fissures in the rock, accelerating until it bursts out of the ocean floor and back into the cold ocean. This is the hypothesis, a place where the deep energetic chemistry of a world's rocky heart meets its vast liquid ocean. And we do not have to just imagine this. We have found these exact places on our own planet. In the 1970s, scientists were exploring the deep Pacific Ocean in a tiny submarine. They were cruising in total absolute darkness, thousands of feet below the surface, in a realm where the pressure is heavy enough to crush a truck. They expected to find nothing but cold, barren mud. Instead, they found chimneys. They saw massive jagged towers, some as tall as office buildings, looming out of the darkness. And from the tops of these towers, a thick black substance was billowing out like smoke from a factory. They named them black smokers. This wasn't smoke. It was that exact process. It was scalding hot water heated by the magma inside the earth erupting from the seafloor. The black smoke was the cloud of dissolved minerals, iron, sulfur, and others instantly cooling and turning solid as they hit the near-freezing ocean water. They called them hydrothermal vents. Hydro for water, thermal for heat. But the most astonishing discovery was not the vents themselves. It was what surrounded them. In this place of total darkness, crushing pressure and water so hot it could melt lead, there was life. And it wasn't just a few desperate microbes, it was a thriving, bustling metropolis. The vents were covered in thick white mats of bacteria. Strange, ghost-white crabs crawled over the rocks. Fields of giant tube worms, some 6 feet long, clustered together, their bright red plumes dancing in the chemical currents. It was an entire ecosystem completely separated from the world of light above. How could this be without a single ray of sunlight? How did this food chain work? They were using a different system, not photosynthesis. They were using chemosynthesis, making things with chemicals. At the very bottom of this food chain were the bacteria. These simple organisms were not eating sunlight. They were eating the chemicals gushing from the vents. They were capturing compounds like hydrogen sulfide, a chemical that smells like rotten eggs and is toxic to us. The bacteria would combine this chemical with the oxygen dissolved in the seawater. This reaction released a burst of energy. The bacteria learned to harness that energy. They used it to build their bodies and to live. And then, everything else ate the bacteria. The crabs, the shrimp, the tube worms, they all survived on this bacterial feast. It was an entire world built not on the light of the sun, but on the chemical energy of the earth itself. This discovery changed biology forever. It proved that life is far more stubborn and far more creative than we ever imagined. It showed us that life doesn't need sunlight, it just needs a source of energy. Now let's go back to our distant moon, back to that dark ocean under the ice. Do you see the connections? It is no longer just a vague hope. It is a blueprint. If life can thrive in the crushing blackness of Earth's deep oceans, feeding on chemicals gushing from volcanic vents, why can't it thrive in the crushing blackness of Europa or Enceladus, or any moon with a hot rocky core and a liquid ocean? These vents are the perfect place. They are protected from the deadly radiation of space by the thick ice shell. The environment is stable. They provide a constant, reliable source of warmth. And most importantly, they provide a steady flow of chemical food and the raw materials needed to build a body. This is the chemical symphony. It is the music that happens when rock and water meet, creating an energy gradient, a difference between the hot chemical-rich water of the vent and the cold plain water of the ocean. Life is what happens in that gradient. Life is the bridge. The possibility of life on these moons is not just a fantasy. It is a logical, scientific possibility based on a model that we have already found right here at home. We have found a potential second genesis, a way for life to begin not in a warm little pond on the surface, but in the hot, energetic darkness of the deep. When we search for life in the universe, we often look for a comforting reflection of ourselves. We look for worlds that are just right, worlds with gentle sunlight, comfortable temperatures, blue skies, and liquid water on the surface. We call this the habitable zone, or more informally, the Goldilocks zone. It's a region around a star where it's not too hot and not too cold, but just right for liquid water. This is a wonderful and intuitive place to start, but it is also deeply biased. It assumes that life must be like us. It assumes that the conditions we find comfortable are the only conditions that life can tolerate. Our own planet, however, screams at us that this assumption is wrong. Earth itself contains environments that are far more hostile, far more alien than the surface of Mars. We find life in places that should be sterile places that would kill a human being in seconds. These organisms are the true champions of resilience. We call them extremophiles, which means lovers of the extreme. But to them, their environment isn't extreme at all. It is simply home. They have not just learned to tolerate these conditions, they have evolved to require them. They show us that the definition of habitable is far wider, far stranger, and far more hopeful than we ever imagined. Let's open this library of survival and meet some of these incredible champions. Imagine the hot springs of Yellowstone National Park. The water is bubbling, steaming, and often at or near the boiling point of water. It is a scalding, seemingly destructive force. Yet this water is teeming with life. We call these organisms thermophiles or heat lovers. For us, heat breaks down the delicate proteins that make our bodies work. Our enzymes unravel like a piece of yarn. But the enzymes of a thermophile are built differently. They are Loctite stabilized, and they only begin to work efficiently at temperatures that would poach an egg. They thrive in heat that we associate with sterilization. Now let's go to the other end of the spectrum, not in temperature but in chemistry. Imagine a place like the Rio Tinto in Spain. It is a river that runs bright red like blood and rust. Its waters are so acidic that they can dissolve metal. The acidity level, what we call the pH or power of hydrogen, is sometimes as low as 2. This is the acidity of battery acid. It is an environment of chemical violence. And yet it is full of acidophiles or acid lovers. These microbes have developed ingenious ways to protect their insides. They have molecular pumps in their cell walls that actively push the acid out as fast as it comes in, maintaining a perfect neutral balance inside while swimming in a bath of acid. What about a place with no fresh water? Consider the Great Salt Lake in Utah or the shores of the Dead Sea. Here the water is hypersaline. It is so saturated with salt that the salt crystals form on the shore. For most cells, this is a death sentence. The salt outside would pull all the water from inside the cell, causing it to shrivel and die. But halophiles, or salt lovers, have a solution. Some balance the salt outside by concentrating salt inside their cells. Others create special protective molecules that hold onto water like a sponge. They flourish in a salty brine that would perfectly preserve and kill any other organism. Finally, let us travel to the most inaccessible place on Earth, the Mariana Trench, the deepest part of our ocean. We must descend nearly 7 miles or 11 kilometers. Down here there is no sunlight. The temperature is just above freezing, and the pressure is staggering. It is over 1,000 times the pressure we feel at the surface. It is the equivalent of having 50 jumbo jets stacked on top of you. This pressure would crush our bones, our lungs, and our very cells. But this is the home of barophiles or pressure lovers. These organisms are not just surviving the pressure, they need it. Their cells and proteins are structured in a way that requires this immense crushing force just to hold them together in the right shape. If you were to bring one to the surface, they would fall apart. This library of survivors teaches us a profound lesson. Life doesn't care about our comfort, but the most important lesson these organisms teach us is not just about conditions, it is about energy. We are obsessed with oxygen. We and the animals we see are aerobic. We breathe oxygen. We use it to burn the fuel, the sugar that powers our bodies. We inhale oxygen, we exhale carbon dioxide. This process is called respiration, and it is very efficient. We assumed for the longest time that complex life must use oxygen. But the extremophiles, and indeed many normal microbes, show us this is just one of many options. Life is just chemistry. To live, you simply need a source of energy. You need a chemical reaction that you can control. For us, the reaction is sugar plus oxygen. But what if you live at the bottom of the ocean at a hydrothermal vent where there is no sunlight and no oxygen? You use what is there. There are microbes that breathe sulfur instead of oxygen. They exhale a compound called hydrogen sulfide, which smells like rotten eggs. To them, oxygen is the deadly poison and sulfur is the breath of life. There are microbes that breathe metal. They take iron compounds, essentially rust, and use them in their respiration. There are methanogens, some of the most ancient life on Earth. They live in swamps or the stomachs of cows. They breathe carbon dioxide and exhale methane gas. Life doesn't need oxygen. It doesn't even need sunlight. It just needs an energy gradient, a high and a low to run its engine. It can use sulfur, iron, hydrogen, or methane. And now we must connect this back to our search. We look at those moons in the outer solar system like Europa and Enceladus. We see worlds covered in ice. We suspect there are vast global oceans of liquid water beneath that ice. But we think, how could life be there? It is dark, there is no sunlight. It is under immense crushing pressure from the miles of ice above. It is likely very, very salty. And the only heat comes from the planet's core, likely creating volcanic vents on the ocean floor. We describe this world and it sounds horrible. It sounds extreme. But now we know better. Dark life doesn't need sunlight, it only needs chemistry. Those hydrothermal vents could be breathing sulfur, or hydrogen right now, salty. The halophiles show us that is not a problem. Crushing pressure. The barophiles of the Mariana Trench would call it home. The champions of resilience on our own planet have completely rewritten the rules. They have not just expanded the habitable zone. They have shattered it. They prove that the extreme conditions of these ocean moons, the high pressure, the salty water, the chemical-rich darkness, are not barriers to life. They are simply another habitat. They are perhaps the perfect opportunity. Let's return to that incredible image, the one that changes everything, the plumes. The geysers of Enceladus, or the suspected plumes of Europa, erupting from cracks in the ice, venting the contents of a hidden ocean out into the vacuum of space. For a long time, these hidden oceans were just a theory, a compelling what-if. But these plumes are messengers. They are carrying samples from a realm we cannot see in an environment trapped under miles of solid ice and spraying them into the open, where our spacecraft can fly right through them. And that is exactly what we did. The Cassini probe, in its long, beautiful dance around Saturn, dove through the plumes of Enceladus. It didn't just photograph them, it tasted them. It used its instruments to analyze their chemical makeup particle by particle. What it found confirmed our hopes in the most astonishing way. It found water ice naturally. It found simple salts, just like the salt in our own oceans. It found tiny grains of silica rock dust, which told us that the water below must be interacting with a hot, rocky seafloor. But then it found the grand prize organic molecules. We must pause here, because this is one of an important and often misunderstood word in the search for life. When we in our daily lives hear the word organic, our minds jump to biology. We think of organic food, living organisms, or something that was once alive. In chemistry, the definition is much simpler and in a way far more profound. An organic molecule is simply any molecule that is built around a scaffold of carbon atoms. Carbon is the great builder of the cosmos. It is an atom with a unique talent for connection. It can form 4 strong, stable bonds with other atoms, and crucially with other carbon atoms. It can build long, intricate chains. It can create stable rings. It can snap together to form the complex 3-dimensional skeletons that all life on Earth uses. The amino acids that build our proteins, the fatty acids that make our cell membranes, the sugars that carry energy, all of these are carbon-based organic molecules. So let's be perfectly clear. Finding organic molecules in the plumes of Enceladus does not mean we found life. It does not mean we found fossils or bacteria or anything biological. What it means is that we found the ingredients. We found the raw materials. We found the specific necessary chemical toolkit that life as we understand it requires to get started. If life is a house, we haven't found the house, but we have found the lumber, the wiring and the pipes all neatly stacked and delivered to the construction site. The next obvious question is, where did these ingredients come from? This is a wonderful cosmic detective story, and there are 3 main possibilities. First, these molecules could be primordial. They might be ancient relics from the very birth of our solar system. The vast cold cloud of gas and dust that collapsed to form our sun and planets was already seeded with simple organic compounds formed in the interstellar medium over millions of years. It's possible that as Enceladus formed, it simply incorporated this pre-stocked material and it has been preserved in its ocean ever deeply. Second, they could have been delivered. For 4.5 billion years, the solar system has been a chaotic shooting gallery. Comets and asteroids, which we know are packed with rich and complex organic molecules, have been constantly bombarding the planets and their moons. Every impact on that icy shell would have delivered a fresh batch of these vital materials, which could eventually melt their way down into the ocean below. The third possibility is to me the most exciting. The molecules might not be old, they might not be imported, they might be being created right now. This theory suggests that the moon itself is an active chemical factory. Let's go back to those hydrothermal vents on the dark sea floor. We have strong evidence for them from the silica dust we found. This is where the ocean water, cold and salty, seeps down into the hot, porous rock of the moon's core. When this water reacts with certain types of rock minerals, a powerful chemical process can occur. One famous version of this is called serpentinization. It's a wonderful name, but the concept is simple rock plus water equals chemical change. This reaction releases a huge amount of energy in the form of heat, and crucially it releases gases, specifically hydrogen. This hydrogen is pure chemical fuel. In the dark pressurized environment of the vent, this hydrogen can react with other simple molecules dissolved in the water like carbon dioxide. Step by step, powered by the chemical energy of the vents, this process, a process that needs no sunlight at all, can build simple molecules into more complex ones. First, it might create methane, then perhaps ethane, and from there the chemical pathways can begin to climb the ladder of complexity, building the very organic molecules that Cassini found. If this is true, it means the moon is not just a passive reservoir. It is an engine. It is actively manufacturing the building blocks of life. Now let's put this all together. Think about what this environment provides. On the surface of a moon like Europa or Enceladus, there is no protection. The ice is blasted by the fierce sterilizing radiation of Jupiter or Saturn. Any complex molecule on the surface would be torn apart in an instant. But under the ice, it is the safest place in the solar system. That thick frozen shell, maybe 10, 20 or even 50 miles thick, is the perfect shield. It blocks all the radiation. It stabilizes the environment, keeping the ocean liquid and safe. It creates a protected realm where chemistry can work its magic undisturbed. This ocean is a prebiotic laboratory. It is a place where for billions of years all the key ingredients have been allowed to mix. We have the liquid water, the solvent. We have the energy flowing from the hydrothermal vents. And now we know we have the building blocks, the organic molecules. What happens when you let water, energy and carbon chemistry cook gently in a dark, protected ocean for 4 billion years? We don't know the answer. But the fact that we have found a place beyond Earth where all the prerequisites for life exist is staggering. We have found an environment where the first crucial steps, the steps that turn simple geology into complex chemistry, are not just possible, but are likely happening right now. The pantry is stocked. The oven is on. The only remaining question is whether that final mysterious spark, the one that turns chemistry into biology, was ever ignited. So let's drift away from the light. We have spent so much of our history understandably looking for life in all the places that feel like home. Places with liquid water on the surface warmed by a gentle star. We search for that Goldilocks zone where it's not too hot and not too cold. But the universe is vast and its creativity is far greater than our own. What happens when we leave the light behind? What happens when we go deep, deep into the rocky crust of a planet, or more tantalizingly deep beneath the miles-thick shell of ice on a moon like Europa or Enceladus? Down there in the absolute crushing dark, the sun is just a forgotten rumor. Photosynthesis is impossible, and yet this may be where the majority of life in the universe actually exists. How does life solve that first, most fundamental problem, the problem of energy? Life is work. It's the work of building cells, of repairing damage, of copying itself. All of that work requires energy. On Earth's surface, plants get that energy from the sun, and we get it from eating plants or eating things that ate the plants. It all comes back to the sun. But in the dark, life had to find a completely different power source. It found chemosynthesis. It's a beautiful word. Instead of photo for light, it uses chemo for chemical. It is life built on the energy stored in chemicals. Think of it this way. To make a fire, you need a fuel like wood or natural gas, and you need an oxidizer, something to burn it with like oxygen. When they combine, you get a release of energy as heat and light. Life in the dark does the exact same thing, but it does it on a microscopic scale, very slowly and very, very carefully capturing that energy instead of just letting it escape as fire. These tiny microbes, bacteria and archaea, are the masters of this. They are chemical specialists. They eat things that we would find completely inedible, even toxic. They find fuel in their environment. Often this fuel is simple hydrogen gas, or it might be methane, or ammonia, or the sulfur compounds that smell like rotten eggs which gush out of hydrothermal vents. And then they have to breathe something. They need their own version of oxygen. This is where it gets truly alien. For many of these microbes, their oxygen is carbon dioxide. Imagine a single microbe floating in the dark ocean beneath Europa's ice. It finds a hydrogen molecule. It finds a carbon dioxide molecule. It has a tiny biological machine inside it, special proteins called enzymes that can take these two things and force them together. The hydrogen and the carbon dioxide react. The end product is methane, which the microbe releases as waste. But the reason it does this, the entire purpose of the transaction, is that this specific chemical reaction releases a tiny spark of energy. It's not much, but it's enough. The microbe captures that spark and uses it to power its life. It uses it to build a new part of its cell wall. It uses it to split in two. It is breathing. It is eating. It is living. All of it powered by a chemical reaction in total permanent darkness. But that just pushes the question back one step. Okay, so the microbes eat hydrogen, but where does the hydrogen come from? If you're trapped in a pocket of water miles deep in solid rock cut off from everything, how do you get a steady supply of fuel? This is perhaps the most profound discovery of all. The answer is radiolysis. It sounds complicated, but the idea is beautifully simple. Rocks are not just dead inert things. Many rocks, like the granite that makes up our own continents, naturally contain tiny, tiny amounts of radioactive elements. Things like uranium, thorium, and potassium-40. They've been baked into the planet's minerals since the solar system first formed. These elements are unstable. and over vast geological timescales they decay. As they decay, they release tiny high-energy particles, a gentle, steady hum of natural radiation. Now imagine this rock is porous, it's cracked, and those cracks are filled with water. Water that has been trapped there for perhaps 1 billion years. When one of these high-energy particles from the decaying uranium zips through that trapped water, it is like a microscopic bullet. It has enough energy to strike a water molecule, an H2O, and crack it apart. It splits the water. And what do you get when you split water? You get hydrogen, the fuel. You also get other more reactive things like hydrogen peroxide. These are the oxidizers. Think about that. The rock itself, just by existing, is constantly and slowly splitting water molecules. It is creating both the fuel hydrogen and the oxygen the oxidizers in the same place. It is a self-contained geological scale battery. It can power a deep dark ecosystem for billions of years, completely totally independent of its star. This process doesn't need a sun. It doesn't even need a planet. It could be happening right now inside a rogue planet, a world ejected from its solar system floating alone in the frozen emptiness between the stars. As long as it has a rocky core and water, it has a source of energy. This brings us to the real secret, the ultimate definition of life and where to find it. It's not just about having the fuel. It's not just about having the oxidizer. It's about having both near each other, but not yet mixed. Life lives at the boundary. It lives in what we call an energy gradient. A gradient is just a difference, a slope. Think of a battery. A battery has a positive terminal and a negative terminal. Nothing happens if you just touch the positive end. Nothing happens if you just touch the negative end. The power is in the flow that happens when you connect them. Life is the wire, life is the circuit. It positions itself right at the boundary and harnesses the flow of energy as these two sides try to come together and find balance. Let's go back to that hydrothermal vent, that black smoker at the bottom of a dark ocean. From below, from the planet's hot mantle, water superheated to hundreds of degrees is gushing out. It is full of fuel hydrogen, methane, hydrogen sulfide. That's the negative terminal. But the cold ocean water above is different. It's full of oxidizers, maybe oxygen or sulfate. That's the positive terminal, positive. Life does not live deep inside the vent. It's too hot and it's all fuel. Life does not live far out in the cold ocean. There's no fuel. Life builds its cities, its thick slimy mats of microbes right on the edge. Right in that turbulent mixing zone where the hot fuel from below crashes into the cold oxidizer from above. It's a habitable zone defined not by light but by chemistry. This is the punchline. When we look for life, we've been looking for places that get just the right amount of sunlight. But maybe sunlight is just one option on a very long menu. Maybe it's the easy high-energy option, the one that allows for big complex things like trees and animals. But it is not the only requirement. The only true universal requirement for life might be this: an energy gradient, a place of imbalance. Life is simply what happens perhaps inevitably when the universe finds a way to bridge that gap. It's a process, a clever way for energy to move from where it is concentrated to where it is not. And that can happen anywhere. In the gentle sunshine of a blue sky morning, or in the absolute crushing black miles beneath a ceiling of ancient ice. But all this talk, all this wondering about extremophiles and quantum life, it can start to feel like a dream, a beautiful complex story we tell ourselves on a dark night. It's comforting to think we are not alone, but where does the dream end and the reality begin? It begins now. It's beginning right at this moment. We are moving past the what if. We are done for now with sitting by the fire and simply telling tales. We have picked up our tools, we have built our vessels, and we have set sail on that dark cosmic ocean. The hunt is on. We are actively searching not with telescopes peering from a distance, but with robots sent on billion-mile journeys to knock on the very doors we've been wondering about. Let's talk about these ships. First, there is NASA's Europa Clipper. Its name tells you everything. It's a sleek, fast and focused machine. Its target is that scratched-up ice-white marble Europa. But Europa Clipper isn't going to land. Landing is incredibly difficult, and we don't even know where the good spots are. Instead, it will do something brilliantly efficient. It will arrive at the Jupiter system and make dozens, nearly 50 close flybys of Europa. It will swoop down, gather a massive amount of data, and then swing back out into the relative safety of Jupiter's orbit, avoiding the most intense radiation. Think of it as a reconnaissance mission. A detective flying past a suspect's house again and again at different times of day with different tools. And what are these tools? It has a radar that can penetrate ice. It's an instrument designed to do something that sounds like science fiction, to look through that frozen crust, which could be miles thick, and find the boundary, to find the top of that hidden global ocean. It will be the first time we can create a map not of the surface but of the depth of the ice. We will finally know if some areas are thin, just a fragile ceiling separating us from that vast dark sea. It also has a thermal camera and instrument that sees in heat. It will scan the surface looking for hot spots. Now hot is a relative term here. It's not looking for a boiling volcano, it's looking for places that are just slightly warmer than the impossibly cold landscape around them. A warmer patch could mean the ice is thin there and the ocean's faint warmth is leaking through. Or even more exciting, it could be the sign of a plume, one of those geysers of ocean water that has just recently erupted and warmed the snow around it. That's the other main goal, find the plumes. Clipper is designed to fly right through them. If it sees a plume erupting from the surface, it has instruments that can taste the spray. It can analyze the molecules in that water and tell us what's in it. Salt organic compounds. The chemical building blocks of life. Europa. Clipper is our first great hope of sampling an alien ocean without ever having to drill. But it's not the only ship on its way. The European Space Agency, ESA, has its own remarkable explorer called JUICE. That's JUICE, which stands for Jupiter Icy Moons Explorer. JUICE has a broader mission. It's a tour of the entire Jovian system, a grand survey. It will study Jupiter's bizarre atmosphere and its faint dusty rings. It will fly by Europa, and it will also study Callisto, that ancient crater giant. But its main focus, its grand finale, will be Ganymede. Ganymede is the ring of moons, the largest moon in our entire solar system, bigger than the planet Mercury, and we now know it too has an ocean. But Ganymede's ocean is different. It's believed to be a sandwich ocean. That sounds strange, I know. But the pressure inside a moon that large is immense. The thinking is that Ganymede has a layer of ice on its surface, then a layer of liquid salt water. But then under that, the pressure becomes so great that the water molecules refreeze into a different, denser, heavier kind of ice. It's not the ice we know, it's Ice 3 or Ice 5, and there may be another layer of liquid water beneath that traps between two layers of ice. JUICE will be the first spacecraft ever to orbit a moon in the outer solar system. It will enter orbit around Ganymede and study it for months. It will try to understand this bizarre sandwich. Does this structure make life less likely? Does it prevent the ocean from touching the rocky seafloor where all the good chemicals and energy might be? Or does this unique geology create possibilities we haven't even imagined? These missions, Clipper and JUICE, are the physical embodiment of our curiosity, but they also highlight our greatest technological challenge. They will tell us about ice thickness, ocean depth and salinity, but they might not be able to answer the big question. The real challenge, the next frontier, is learning how to detect biosignatures. This is a crucial word. A biosignature is not life itself. It's the shadow life leaves behind. It's the footprint by the water's edge. When you breathe out, you release carbon dioxide. That is a signature of your metabolism. Plants release oxygen. That is their signature. On Earth, vast communities of bacteria produce methane. That is their signature. We are not looking for a fish. We are not looking for a bacterium. We are looking for a chemical imbalance. We are looking for a specific complex molecule that nature would have a very, very hard time making by accident. We are looking for the byproducts of metabolism. This is incredibly difficult. How do you build a machine that can tell the difference between a chemical made by a living thing and the exact same chemical made by a non-living process, like a strange reaction in a hot deep-sea vent? How do you make that instrument small enough to fit on a spacecraft, robust enough to survive a 10-year journey through a vacuum, and sensitive enough to detect a handful of molecules in a blast of ice? That is the true hunt. It's not just about finding water. We found water. It's about building the tools to find the evidence. We are no longer just astronomers. We are becoming cosmic biologists, interplanetary detectives, and we are at long last finally on our way to the crime scene, instruments in hand, ready to start the investigation. And so we find ourselves peering into the most extreme corners of our own world, looking for the limits of life, only to find that they stretch further than we ever imagined. We find life in boiling acid, in the crushing dark, in the frozen stillness. And this hunt, this search for the boundary, isn't just about cataloguing strange creatures. It is practice. It's training for the day we look elsewhere. But let's pause our search for a moment. Let's step back from the microscope and the deep-sea submersible and the Mars rover. Let's just imagine. What if we succeed? What if in the muddy ice of Europa's hidden ocean, or in the methane haze of Titan, or in the dried-up riverbeds of Mars we find something, not a fossil, not a chemical signature, but something living, a cell, a microbe. What happens to us then? It wouldn't just be a scientific discovery, it wouldn't just be a headline, it would be a philosophical realignment of our entire species. For all of our recorded history, we have operated under the assumption that we are special, unique, a singular miraculous event, a random lightning strike in a specific primordial soup on a specific planet. Our religions, our philosophies, our loneliness, it's all been built on the foundation that we are the sole occupants of the thinking universe. But if we find life, even the simplest microbe out there, that foundation cracks. It suggests that life is not a miracle. It is normal. It's what the universe does. It suggests that the cosmos, given the right ingredients, carbon, water, energy, time, will perhaps inevitably begin to organize itself. That life is not a violation of the laws of physics, but a consequence of them. It would mean that the universe is not a sterile, dead expanse with one tiny accidental green oasis. It would mean the universe is a garden, and we are not the only flower. This is a beautiful, hopeful thought, but this new understanding, this idea that life is common, immediately slams us into a wall. A vast, silent one. We call it the Fermi paradox, the great silence. The paradox is simple. If life is common, then intelligent life must also be common, or at least it must have happened somewhere else. Our galaxy alone is 100,000 light-years across. It contains perhaps 400 billion stars. It has been around for over 13 billion years. That is more than enough time and more than enough real estate for someone to have developed, to have grown, to have surpassed us, and to have started travelling. So where is everybody? If the universe is constantly producing life and it's had billions of years of a head start on us, why is it so quiet? Why haven't we been visited? Why don't we see the signals of vast starfaring empires? Why don't we see their giant engineering projects, their Dyson spheres, their star-fueled machines? The sky is silent. This silence in this context becomes louder. It becomes a puzzle, and the possible solutions are deeply unsettling. This has led to a sobering, almost chilling idea. It's called the Great Filter. The concept of the Great Filter is this: for life to go from simple cells to a galaxy-spanning civilization, it must pass through a series of gates or filters, and one of those gates must be almost impossible to get through. The question is, where is that filter? We can be optimistic and say the filter is behind us. Maybe the hardest step was the first one. Maybe the spontaneous generation of life from non-life is so outrageously improbable that it has only happened once, here, and we are the first. Or maybe the filter was the jump from a simple cell to a complex one. That step took nearly 2 billion years on Earth. Perhaps that is the bottleneck. But what if the filter is ahead of us? What if, as many suspect, the filter is the tendency for intelligent species to discover technology like nuclear power or artificial intelligence that they cannot control? What if every civilization upon reaching our stage of development inevitably destroys itself? That would explain the silence. The sky is quiet because the civilizations are by their nature self-limiting. They burn bright and then they burn out. There is, however, another possibility, a quieter one. What if the galaxy is teeming with life, but it's almost all bacteria? What if the universe is a vast cosmic ocean of simple single-celled organisms swimming in the dark and complex life plants? Animals, thinking beings, is the real anomaly. In this view, we are not the rule. We are the profound exception. The universe is a vast ocean of simple life, and we are the first strange, complex creature to crawl onto the beach, look up and wonder where everyone else is. This brings up a fascinating problem. What if we find life on Mars, but it just confuses the issue? This leads us to the concept of panspermia. Panspermia, it's a beautiful word. It literally means seeds everywhere. The idea is that life isn't necessarily born on every planet, it just travels between them. Think about it. A massive asteroid or comet hits a planet, say Mars, back when it was wet and alive. The impact is so violent that it throws rocks saturated with microbes deep into space. These tiny, hardy organisms, like the extremophiles we discussed, go dormant. They freeze, they are battered by radiation, but they survive. For thousands, maybe millions of years, this rock tumbles through the void, until one day it is caught by the gravity of another planet. A blue-white one, it streaks through the atmosphere and lands. The microbes thaw out in a new welcoming ocean and life begins anew. This means that if we find microbes on Mars, they might just be our cousins, or we might be the Martians. Life on Earth might be an alien immigrant. If that's true, then all life in our solar system shares a single origin. So how would we ever know? How could we tell the difference between a long-lost cousin and a true independent second genesis? We would look at its hands. I mean that almost literally. We would look at its chirality, which is a Greek word for handedness. Look at your own hands. They are mirror images of each other, but they are not identical. You cannot perfectly superimpose one on the other. You can't put a left glove on a right hand. Molecules, especially the complex molecules of life, have this same property. Amino acids, the building blocks of proteins, can exist in two forms, a left-handed version and a right-handed version. Chemically, they are identical, but structurally they are mirror images. Now here is the strange part. Life on Earth, all of it from the bacteria in the vent to the blue whale in the sea, to the cells in your own body, made a choice. Our amino acids are all left-handed. Our sugars are all right-handed. There is no chemical reason it had to be this way. It was seemingly a 50-50 coin toss, but once that choice was made, all life followed it. It's a shared chemical signature for every living thing on our planet. So here is the test. If we go to Titan and we pull a microbe from that freezing methane sea, and we look at its chemistry, and we find that its amino acids are right-handed, or what if it doesn't even use the same amino acids? We use a specific set of 20. What if it uses 100? Or what if it doesn't use water as its solvent but liquid methane? That is the moment. That is the discovery. Okay. That is a second genesis. It would be the single most profound discovery in human history because it would answer the biggest question. It would prove that the universe is not just alive, but that it's creative, that it has invented life more than once. Finding life would be profound. Finding a second kind of life would change our definition of the universe. It would mean the cosmos is not a sterile desert with one lonely oasis. It's a creative ocean, a laboratory constantly experimenting, and that life is the music it makes. We have spent a great deal of time painting the universe as a microbial sea. We have imagined countless worlds where the only life is a thin, simple film of single-celled organisms clinging to a rock, feeding on a trickle of chemicals, or basking in the light of a distant star. In this vast cosmic ocean, the overwhelming majority of all life everywhere is almost certainly microbial. It's the simplest, most robust, and most adaptable form life can take. But is that the end of the story? Is that all the cosmos has to offer? Is the universe a library filled with only one book copied 1 trillion times? Or does life, given the chance, try to write something new? Does it try to build you up? This is the question of complexity. Is it all just microbes, or can life organize itself into the fantastic, sprawling, multicellular forms we see here on Earth? Can it produce the equivalent of a plant, a fungus, an insect, or even perhaps something that thinks? The case for multicellularity is, in a word, strong. The most powerful piece of evidence comes from our own planet. Life did not just discover how to be complex once, it discovered it many, many times completely independently. Think about what we are. We are an animal. Every animal on this planet, from a sponge to a sparrow, shares a common ancestor that made this leap. But plants made the leap all on their own, from a different single-celled ancestor. Fungi did it again a third time. Different kinds of seaweed, like the giant kelp forests, represent other independent experiments. Even some slime molds in their strange life cycles decide to come together and act as a single large organism for a time. When something evolves over and over again independently, it has a name. We call it convergent evolution. It means that this isn't a 1 in a trillion miracle. It is a good idea. It is a solution that life naturally stumbles upon when the conditions are right. Why is it such a good idea? Because of specialization. A single cell has to do everything. It has to eat, breathe, reproduce, move, and defend itself all in one tiny package. But in a multicellular community, cells can specialize. One cell can become a sin cell, focusing only on protection. Another can become a stomach cell, focusing only on digestion. Another can become a nerve cell, focusing only on communication. This division of labor is incredibly efficient. It's the difference between a single person trying to build a house and a dedicated team of carpenters, plumbers, and electricians. Together, they can build something far larger and more sophisticated than any one of them could alone. This cooperation allows life to grow large, to move with purpose, and to exploit new environments. The evidence on Earth suggests that this leap is not just possible, but perhaps even probable given enough time. But it requires one thing above all else. It is the same requirement for building any complex long-term project: stability. To build a complex body, you need a reliable, stable source of energy that persists for geological time. Evolution does not work in a hurry. It took over 3 billion years for Earth to go from its first cell to its first simple animal. This could only happen because our planet had a safe harbour. It had a sun that burned with incredible stability. It had an orbit that kept the temperature within a mostly liquid range. It had a steady, reliable flow of energy. If a planet's environment is too chaotic, if its star flares violently or its orbit swings wildly, or its geothermal energy sputters and dies, life is constantly reset. It's thrown back to the starting line, forced to remain in that simple, tough microbial form just to survive. But if you have a world with a long-term stable energy gradient, a steady, deep river of energy, be it from a star or from a planet's own internal heat, then evolution has a canvas. It has the time and the resources to tinker. It can experiment with new forms. It can afford the cost of building specialized cells and complex bodies. It can begin the slow, magnificent process of building something more. So let's imagine. Let's speculate on what this life would be like. Forget the sunlit surfaces for a moment. Let's journey to a place we have discussed before, a Europa world, a planet or moon covered in a thick shell of ice hiding a vast dark liquid water ocean. We know these places likely have stable energy. The tidal forces of a giant nearby planet could knead the core, keeping it hot, driving volcanic vents on the seafloor for billions of years. This is the stability life needs. This is the steady energy gradient. So microbial life is almost certainly there feeding on those chemical plumes. But after 1 billion or 2 or 5 billion years, what else? The first thing to understand is that this is a world of eternal darkness. Light is not a concept. Light from the distant star does not penetrate miles of ice. Therefore, eyes are a complete waste of energy. Vision, the sense that so profoundly defines our own experience, would simply not exist. So how would a complex organism see its world? It would see through pressure. In an ocean, your entire body is a sensor. You can feel the weight of the water above you telling you your exact depth. You can feel the push of a current. More importantly, you can feel the movement of other things. A large creature swimming nearby would create a shockwave, a subtle change in pressure that you could feel long before it reaches you. It is a form of 3D sonar using the water itself as a medium. It would see through chemistry. This is the sense of taste and smell amplified to a degree we can barely imagine. The water would be an ocean of information. A chemical plume from a hydrothermal vent isn't just food. It has a shape, a direction, a temperature. You could follow it like a bloodhound. A predator might release a chemical scent to mark its territory. A prey item might release a cloud of fear chemicals when attacked. You might even find mates by tasting their unique chemical signal in the water from miles away. And perhaps most alien of all, it would see with electricity. Water, especially salty water, is an excellent conductor. Every time a muscle moves or a nerve fires, it creates a tiny faint electric field. On Earth, sharks, eels, and even the platypus have evolved electroreception. They can sense these fields. In an ocean of total darkness, this would be the ultimate sense. A predator could see the electric pulse of its prey's beating heart, even if it was buried in the mud. Life itself would glow not with light, but with a bioelectric aura. This leads to a final profound realization. Life in such a place would have a different rhythm. Without the high-energy blast of a sun, metabolism would be slow. Life would be cold. Everything would happen at a glacial pace. In the cold, dark deep, creatures would grow slowly live for immense periods and move with a deliberate, patient grace. Our lives are frantic. We are hot creatures dictated by the 24-hour spin of our planet. We are born, we live, and we die in a flash. But life in that deep, dark ocean, it would be ancient. A creature might live for 10,000 years. A thought for a conscious being in that realm might take an hour to form. A conversation carried on clouds of released chemicals might take a century to complete. They would be slow, old, and contemplative. If we were to ever meet them, they might not even perceive us as alive. We would be a blur, a flash of heat and energy that is born and dies in the blink of their ancient, unseeing eyes. They would be the true patient observers of the cosmos, existing in a world of pressure and taste in a rhythm that matches the slow, steady pulse of their planet's core. We have journeyed through the cosmos, exploring the raw materials of existence, the elements forged in stars, the molecules drifting in space, the water that flows on distant moons. We have talked about chemistry, the carbon, the heat, and the rock. But this brings us to the most profound question of all. When does a pile of wet carbon-based chemicals stop being just chemistry and start being alive? What is life? It is not just the stuff. After all, the atoms in your body are constantly being replaced. The you of today is not made of the same physical matter you were a decade ago. The matter flows through you like water through a riverbed. You are not the water, you are the pattern the water follows. Life in its deepest essence is not chemistry, it is information. It's a system that has found a way to store, process, and replicate a set of instructions. The chemistry is just the medium. It is the ink and the paper. Life is the story written with that ink. It is the blueprint that tells the raw materials how to organize themselves into a bacterium, a redwood, or a person. The real mystery of life is the origin of this code. On Earth, this system is magnificent and it is singular. The blueprint for all life we know is stored in a molecule called deoxyribonucleic acid, or DNA. It is a long twisted ladder, the famous double helix. It stores its information in a code of just 4 chemical letters, A, T, C, and G. With these 4 letters, it writes the manual for every living thing from the simplest virus to the most complex mammal. This DNA is the master library locked away and protected. To actually use the information, the system relies on a partner ribonucleic acid, or RNA. RNA is like the working copy of the messenger that takes a single instruction from the library to the factory floor where it builds the proteins that do all the work of being alive. This DNA called RNA system is the foundation of every single living organism we have ever discovered. It is the one universal language of biology on this planet. It is so universal, in fact, that it creates a powerful bias in our thinking. We see that it works so well and we see it everywhere, and we begin to assume that this must be the only way. This leads us to the big question, perhaps the most important question in the search for life elsewhere. Is DNA the only solution? Is this intricate, beautiful molecule the one single inevitable answer that the universe finds whenever it wants to create life? Or is it just our answer? Is it a local innovation, a biological system that cornered the market on this one planet, simply because it got started here first? When we send probes to Mars, or when we dream of drilling into the oceans of Europa or Enceladus, what are we looking for? If we are only looking for DNA, we may be missing the forest for the trees. If the core of life is information, then surely there must be other ways to store it. In our own technology, we store information on magnetic tape, on silicon chips, on etched plastic disks. The medium is different, but the data, the ones and zeros, is the same. Why should biology be any different? Could life on another world use a different kind of ink? This isn't just a philosophical question anymore. Right here on Earth, in our own laboratories, scientists are proving that the answer is yes. They are actively creating alternatives. This brings us to the introduction of XNA, which stands for xenonucleic acids. Xeno is simply the Greek word for foreign or alien. These are synthetic molecules designed by humans that are relatives of DNA, but not DNA. Scientists can take the basic ladder structure but replace the backbone. The deoxyribose sugar that gives DNA its name can be swapped out for a different chemical structure entirely, and the results are revolutionary. These new XNA molecules, which have never existed in nature, have been shown to do the 2 key things that life requires. First, they can store information. They can hold the same TCG letters, or even new synthetic letters. And second, this is the critical part, they can evolve. Scientists have successfully created XNA enzymes that can act on other molecules, and they have guided them through laboratory-based natural selection to become better and better at their jobs. They can even be made to copy themselves. This is life, or at least its core mechanism in a test tube, using a chemical blueprint that is fundamentally alien to our own. This work proves that the concept of a genetic polymer is not unique to DNA or RNA. The universe has a much wider palette to paint with than we ever knew. So if we cannot assume we will find DNA, what is the real biosignature? What do we look for in that ice on Europa? The answer is simple. We must start looking for order. We look for patterns and complexity that random chemistry alone cannot explain. The key is to look for polymers. A polymer is just a long-range chain made of repeating molecular units like beads on a string. Plastic is a polymer, the cellulose in a tree trunk is a polymer, and our DNA is a polymer. On a dead world, chemistry is messy and random. You might find the beads, the building blocks like amino acids, but they will be in a jumbled chaotic. Life, however, is a selective process. Life is not random. It doesn't just grab any bead from the pile. It carefully selects specific beads and strings them together in a very specific order. It does this because that specific order means something. It's a code. It's an instruction. If we analyze a sample from Mars and find only a random jumble of simple molecules, that is geology. But if we find a long-chain polymer, any polymer made of the same repeating subunits strung together in a complex, non-random pattern, that is a revolutionary discovery. It's the difference between finding a handful of random letters scattered on the ground and finding a sentence. That sentence implies a writer. A non-random polymer implies life. And there is one more incredibly powerful sign of this ordering process. It is a beautiful and subtle concept known as chirality, or handedness. Many of the essential molecules of life, like the amino acids that build our proteins, are like your hands. Your left hand and your right hand are perfect mirror images of each other. They have the same parts of thumb, 4 fingers, but they are not identical. You cannot put a left-handed glove on your right hand. They are non-superimposable. When these molecules are created by random non-living chemistry in a test tube or in a meteor strike, you always get a 50-50 mix of the left-handed and right-handed versions. This is called a racemic mixture. But life chooses. For reasons we still don't fully understand, life on Earth made a choice billions of years ago. To build stable functional machines like proteins, it needed standardized parts. Imagine trying to build a spiral staircase if every other step was angled the opposite way. It would be a chaotic, non-functional mess. So life on Earth settled on one. All of the amino acids used in life on Earth are left-handed. Almost all of the sugars, including the sugar in DNA and RNA, are right-handed. This is called homochirality, a preference for only one hand. This provides us with one of the most powerful and universal biosignatures we could ever look for. If we find a pool of amino acids on another world and the mix is 50-50, that is just geology. But if we find a pool where all the amino acids are left-handed, or just as excitingly if all of them are right-handed, that is a definitive sign. That is a biological siren flashing in the darkness. It tells us that a selective process has been at work. It tells us that something has moved beyond the chaos of simple chemistry and into the organized information-based realm of life. Here we are. We have crossed the solar system. We have peered into the darkness and found warmth. We've identified these incredible, impossible oases hidden beneath shields of ice. We've talked about the kind of life that could exist there, the tough, stubborn, radiation-eating, cold-loving life that thrives in Earth's own extremes. The excitement is overwhelming. We are perhaps standing on the threshold of the single greatest discovery in human history, the confirmation that we are not alone. But this discovery brings with it a dilemma. It is perhaps the most profound ethical and technical challenge our species has ever faced. We are standing on the shores of a cosmic ocean, but we are a creature of the land, and we are dirty. The very act of reaching out to see if anything is in that ocean could be the act that destroys it. This is the great, terrible problem of forward contamination. Think of it this way. Imagine you are an explorer and you discover a small isolated island in the middle of the Pacific Ocean. This island has been cut off from the rest of the world for 10 million years. The plants, the insects, the birds, they have all evolved in a completely unique way. It is a perfect, pristine ecosystem. Now imagine you decide to land, but your ship isn't clean. The moment you step ashore, you accidentally release rats from the cargo hold. You track in seeds from a dozen different continents on your boots. You sneeze and introduce a virus that the local wildlife has no immunity against. Within a decade, the island's unique ecosystem has collapsed. The native birds are gone eaten by the rats. The native plants are choked out by invasive weeds. You didn't mean to do it. You were just curious. You just wanted to look, but your mere presence was a catastrophe. Now multiply that by 1 billion. We are the explorers. The ice moons of Jupiter and Saturn are the islands, and we are covered inside and out with the most invasive, most aggressive, and most resilient life form we know, life from Earth. Our spacecraft, no matter how carefully we build them, are contaminated. They are built by human hands in factories on Earth, breathing Earth air. They carry a bio-load of our world. We are talking about bacteria, viruses, and most importantly, spores. Spores are the escape pods of the microbial world. They are tiny, dormant, and almost indestructible. And this is where our previous discussion comes back to haunt us. The very extremophiles we studied, the ones that prove life can survive the vacuum of space or intense radiation or being frozen for thousands of years, those are the exact hitchhikers we are terrified of. A single bacterial spore from Earth tucked away in a microscopic crack in a landing strut could survive the journey. It could land on Europa. It could survive the cold, the radiation. And if it finds its way into that liquid water ocean, an ocean that has been sterile for 4 billion years, what happens? If that ocean has no life, our microbe might find a buffet of chemical energy and no predators. It could over thousands or millions of years claim the entire ocean for itself. We would have seeded that world with Earth life, and it would forever be impossible to know if life ever would have started there on its own. But the other scenario is even worse. What if there is native life in that ocean? What if it's simple, slow-moving and fragile? Our little spore, born from the hyper-competitive kill or be killed environment of Earth, would be like a shark in a goldfish pond. It could outcompete the native life. It could consume its food source. It could even be toxic to it. We might, in our clumsy search for life, wipe out the very life we were looking for. We would be cosmic vandals destroying a second Genesis before we even had a chance to say hello. We would never know what we had done. This isn't science fiction. This is the single biggest fear holding us back. We have protocols, of course. We have an entire field of study called planetary protection. We do everything we can to sterilize our probes. We bake the spacecraft in giant ovens, cooking them at incredibly high temperatures for days to kill everything we can. We bathe components in harsh chemicals. We blast them with radiation. We assemble them in clean rooms where the air is filtered more thoroughly than in an operating theatre, and the technicians are covered in suits looking like astronauts themselves. But here is the terrifying truth: we cannot achieve 100% sterility. It's not possible. Life, as we've learned, is just too stubborn. We can reduce the number of spores down to a few hundred, maybe a few dozen, but we can't get it to zero. And so we are paralysed. We have the technology to get to Europa. We are designing the drills that can melt through the ice. But should we use them? This is the conflict. It is our boundless defining curiosity versus our newfound awesome responsibility. What right do we have to risk an entire world just to satisfy our own need to know? This is the dilemma, but it has a twin, a darker, more selfish fear. Let's flip the scenario. Let's say we do it. We build a perfect sterile probe, we drill through the ice, we take a sample of that alien water, and it is teeming with life. Microbes, alien microbes. And then we bring it home? This is backward contamination. This is the plot of 100 horror movies, but it's a real concern for NASA and other space agencies. What if we bring something back to Earth that is harmful to us? Now most biologists think this risk is very, very low. An alien microbe would be evolved for an alien environment. It would have no idea how to infect a human cell any more than we know how to infect a rock. It would be designed to eat chemicals we don't have in temperatures we don't live in. Our own immune systems would likely see it as just weird dust. But very low risk is not zero risk. What if it's not harmful because it's a predator, but because its waste products are toxic? What if it just loves the taste of plastic? We don't know. The chance is small, but the consequences are absolute. If we were to accidentally release a microbe that could, for example, eat a vital crop, it would be an irreversible disaster. This is why any sample return mission from a place like Mars, let alone Europa, is planned with extreme quarantine procedures. The sample would be treated as the most dangerous substance in the universe, locked away in special labs handled by robots and studied for years before we were sure it was safe. So this is where we are. We stand at the edge of the water. We are afraid to contaminate it, and we are afraid of it contaminating us. This is the great pause. We are the generation that found the oases. We are also the generation that must decide whether to drink from them or to leave them be forever, as beautiful, mysterious, and untouched wonders in the dark. This choice, this dilemma, is about more than just technology. It's a test of our wisdom. It's a measure of our maturity as a species. Are we just clever animals grabbing at whatever we can reach, or are we something more? Are we ready to be good ancestors? And so we find ourselves circling back to an idea we touched on earlier, a concept that feels both ancient and futuristic, the idea of panspermia, the scattering of seeds across the cosmos. Perhaps this is the most fitting place to rest our thoughts as our journey comes to a close, because this idea, more than any of theirs, forces us to ask the ultimate question, not just of what we are, but where we are from. Are we the singular, brilliant, lonely miracle of a single planet? Or are we the children of a much larger cosmic family? This isn't just a fantasy, or there are clues. Little breadcrumbs scattered through our own solar system that make us wonder. We have found rocks on Earth here in our hands that we know for a fact came from Mars. They were blasted off the red planet by an ancient asteroid impact and drifted through space for millions of years before falling on our world. And in at least one of these Martian meteorites, scientists found tiny, tiny structures that looked familiar. They looked like microscopic fossilized bacteria. Now are they? The debate has raged for decades. The evidence is not conclusive. They could just be strange mineral formations, but they could be the first sign. A little hello from a neighbouring world. It opens the door just a crack to the possibility that life can travel between planets. And then we look at life itself, our life. We test its limits. We are astonished by its stubbornness. We've taken tiny, simple organisms, bacteria spores, even microscopic animals called tardigrades, the little water bears, and we have attached them to the outside of rockets. We have exposed them to the worst the universe has to offer, the absolute zero of the void, the unfiltered, blistering radiation of the sun, the hard vacuum of space. And when we brought them back, some of them woke up. They survived. Life is not the delicate flower we often assume it is. It is a resilient, stubborn weed capable of clinging to existence in the most hostile environments imaginable. If it can survive the outside of a spaceship, could it survive a journey of thousands or millions of years frozen deep inside a chunk of rock? It seems plausible. And where would these seeds come from? We look to the comets, those beautiful icy visitors from the deep to dark. We have flown spacecraft through their tails. We have landed probes on their surfaces, and we have found they are not just dirty snowballs. They are packed with the building blocks of life, complex organic molecules, amino acids, the very same components that make up the proteins in your own body. These comets and asteroids which we once saw as agents of destruction might actually be the cosmic delivery service seeding fertile planets with the essential ingredients and maybe, just maybe, with life itself. This leads us to two possibilities, two ideas so profound they almost stop the mind, and one of them must be true. Imagine for a moment that we do it. We send a probe to the ocean beneath the ice of Europa, Jupiter's moon. We drill down, we dip a microscope into that dark alien water, and we find something. It's alive, it's swimming. We study it, and we find it has DNA, or something very, very similar. We find that its basic chemistry, its cellular machinery is built on the same fundamental blueprint as ours. What would that mean? It would mean we are not alone, not in the deepest sense. It would mean that life, our kind of life, has spread. It would mean panspermia is real. It would confirm that the life on Earth and the life on Europa are related. We would be family, cousins separated by hundreds of millions of miles of empty space, but originating from the same ancient spark. We would be part of a single solar system-wide and perhaps even galactic family tree. We would know that life is not just here, it is out there, and it is us. Now, imagine a different scene. We drill through that ice, we find life, but when we look at it, it is baffling. It has no DNA. It doesn't use proteins or amino acids as we know them. Its cells, if they are cells at all, operate on a chemical principle we have never seen before. It is built from a completely different set of blocks. It is a truly alien life. This in its own way is an even more staggering discovery. This would mean that life is not a single lucky accident that spread. It would mean that life is a fundamental property of the universe. It would mean that wherever the conditions are right, liquid water, a source of energy, the right chemicals, the universe creates. It's a cosmic imperative. Life is something that the cosmos does. If this were true, it would imply that the universe is not just dotted with our relatives, it would be overflowing with a countless unimaginable diversity of creations. It would mean there was a second Genesis, a different tree of life right in our own backyard. And if it happened twice here, just in our little solar system, how many times has it happened out there among those billions of other stars the universe would be revealed as a garden of infinite unique forms? This is where our search has led us. From the smallest particle to the largest galaxy, from the first second of time to this present moment, we are left staring at this ultimate question. It makes us reconsider what life even is. We have spent this whole time thinking of life as a thing, a noun, a collection of cells, a plant, an animal, a person, but maybe that's the wrong way to look at it. Maybe life is not a noun but a verb, a process. It is a pattern, a slow, persistent cosmic fire. It is the universe's way of organizing complexity. It is a way for matter to become self-aware, to look back at the stars that made it. And this process, it is patient. It unfolds over timescales we can barely imagine. It is resilient. It survives impacts and ice ages and the vacuum of space. It is quiet. It is not loud or flashy. It is a subtle, slow unfolding. It could be happening right now in total silence in the blackness of an ocean under miles of ice. It could be happening in the methane lakes of Titan or the clouds of Venus, or in the dusty heart of a nebula generations before a planet is even born. Life is a process, and it is waiting. It is waiting quietly in the dark under the ice in the clouds for us to finally build the tools to travel the distance, to be quiet enough ourselves, to listen, to find it, to find our family, or to find at long last our neighbours.